We now arrive at the subject of an amino acid's isoelectric point, which is abbreviated as pi. Magnum pi. No, I'm just kidding. It's just regular pi. Simply defined, an amino acid's isoelectric point, or pi, is the pH at which that amino acid has no net charge. Let's take a look at this example. If we look at alanine, this amino acid right here, in the form shown here, we can see that it has a negative charge on the oxygen and a positive charge on the nitrogen. What's its net charge? Well, 0, of course, because +1 and -1 cancel each other out. That's what I'm talking about when I say that an amino acid's isoelectric point is the pH at which it has no net charge. I'm saying that the pH at which the amino acid's net charge is 0 is that particular amino acid's isoelectric point. Okay. So how do we calculate an amino acid's pi? For amino acids that don't have acidic or ionizable side chains, it's just the average of their OH and NH3 plus pKa values. Let's take the example of alanine. Shown here, you can see that alanine's pKa for the carboxylic acid OH is 2.34. The pKa of the amine group is 9.69. Because alanine does not have an ionizable side chain, that is, it doesn't have a side chain that you could protonate or deprotonate or that can act as a base or an acid. It's just got a boring old carbon side chain. Because that's the kind of side chain it has, the isoelectric point pi is just the average of these two pKa values. That's it. So I just take 2.34 plus 9.69, get a number, 12.03, and divide it by 2. That number, 6.02, is alanine's isoelectric point pi. So what in the world does that mean? Simply put, it means that at pH 6.02, alanine will exist more or less completely in this form right here, having no net charge. Below pH 6.02, you might remember there's more and more H plus around, which means that we're going to protonate this O minus to some degree. If you protonate this O minus, you get rid of the minus charge. So what is alanine's net charge at low pH? It's +1. At higher pH, we start to see less and less H plus around, and eventually we deprotonate this NH3 plus and turn it into an NH2. So if you have a neutral NH2 here, what is alanine's net charge? It's -1. So once again, at pH 6.02, which is alanine's isoelectric point, it will exist exclusively in this form. As we get lower and lower pH, we start to protonate this O minus, which gives alanine more and more a net +1 charge. As we get higher and higher pH, we start to deprotonate stuff. We remove one of these protons off of the NH3 plus, making it an NH2, giving alanine an overall net -1 charge. I hope that makes sense okay. Now we arrive at the magical question, issued really by me, but hopefully also by you, my nebulous internet student. How do we calculate the pi for an amino acid with an ionizable side chain? What's the answer? Well, you calculate the average pKa values of the two ionizable groups that have the same charge as each other, obviously. Now I assume that if you're like me, you're probably right now looking at this statement and thinking, what? Okay. Let's do some examples to hopefully solidify this. We'll start by looking at lysine, which has this structure. I'll ask you this question. If we look at this molecule's ionizable groups, which are this OH, this NH3+, and the other NH3+, which ones or which two of these groups have the same charge as each other? Does the OH have the same charge as an NH3+? No. Does this NH3+ have the same charge as this OH? No. So which two groups have the same charge as each other? It's these two NH3+. They both have a +1 charge, don't they? So how do we calculate lysine's pi? We take the average pKa value of the two NH3+ groups, that is, the two groups that have the same charge as each other, and we completely ignore the OH. So let's see if we can do that. Here we've got the pKa value of this NH3+ and the pKa value of this NH3+. We need to calculate the average. We just add them both together, giving us a 19.74, and divide them by 2. That gives us 9.87. So once again, what in the holy bleep does that mean? It means that at 9.87, lysine molecules in solution will exist in a state that has no net average charge. Below pH 9.87, lysines will become more and more positively charged. And above pH 9.87, lysines will become more and more negatively charged. That's what it means. Let's do another example. Here's glutamic acid. Once again, I ask the question, which two ionizable groups have the same charge as each other? Once again, I'm looking at the two OHs here and the NH3+. Those are the ionizable groups. In this case, I only have one NH3+, and I've got two OHs. So the NH3+ here, in this case, is the odd man out. So for lysine, we calculate the isoelectric point by taking the average pKa values of the two OH groups, and we ignore the NH3+. And now I re-emphasize what I said in the previous slide. The isoelectric point is the pH at which this molecule has a net average charge of 0. If we calculate this thing out, we take 2.19, 4.25, add them together. We get 6.44 divided by 2, and the isoelectric point of glutamic acid becomes 3.22. So that means that at pH 3.22, glutamic acids in solution will exist in a state that has no net average charge. Below pH 3.22, glutamic acid will become more and more positively charged. And above pH 3.22, glutamic acid will become more and more negatively charged. Are you ready for some examples? Good. So I want you to calculate the isoelectric point, or pi, of each of the following amino acids. I should give you a hint. You're going to have to use the pKa table found on table 23.3 in your book, and also found in our earlier PowerPoint lecture on this chapter. But don't worry, I'm going to guide you through this problem over the next few slides and do a couple of these examples with you. I'll let you do the rest, of course. So here's my step-by-step formula on how to calculate an amino acid's isoelectric point. Step 1. Draw the molecule fully protonated. That is, with all of its carboxylic acid groups as OHs, its amide groups as NH2s, and its amine groups as NH3+. For our first example, asparagine, that's what it's going to look like. I have an amide group over here, I just leave it as an NH2. NH3+ on the amine groups, and OHs as OHs instead of O-. That's step 1. Step 2 is using the information on table 23.3, we write down the pKa values for each OH and NH3+. Amide NH2s do not have pKa values on table 23.3. What are those pKa values for asparagine? Here they are. Step 3. If you only have 2 pKa values to work with, then just calculate your average, and you're done. Here's the average between these two pKa values. 2.02 plus 8.84 divided by 2 gives us 5.43 as the isoelectric point for asparagine. Step 4. Remember what that number actually means. It means that at pH 5.43, asparagine will have a net zero charge. What that means is that right at that pH 5.43, asparagine will have an NH3 plus here and an O minus over here. So it will have a net zero charge. Below that pH, we'll start to see OHs, or the O minus is getting protonated. So we'll start to see it look like this form. It will have a net positive charge. Above that pH, we'll start to see more and more NH3 pluses get deprotonated to give neutral NH2s, with O minuses being here, giving us a net -1 charge. Alright, let's do another one. Remember my steps. Step 1. Draw the molecule fully protonated. Arginine's kind of a weirdo. We have to protonate this group over here that has 2 amines coming off of this carbon. One of them has a double bond. We leave, of course, our NH3 plus is protonated and our OH is protonated as well. Step 2. Write down the pKa for each applicable group. What are those pKa's for this molecule? They are these. Step 3. If you have more than 2 pKa's, and we do in this case, then find the 2 that have the same charge. I'm going to pause here for a minute and look at that. I have an OH, no charge. I've got an H2 plus and an H3 plus. They both have a +1 charge. These are the 2 groups that have the same charge. Then I calculate the average of those 2 groups' pKa values, which is this: 9.04 plus 12.48 divided by 2, 10.76. Step 4 is remember what that means. What that means is that arginine at pH 10.76 will exist in a state that has a net 0 charge. Below that pH, we start to protonate stuff, including this OH, so we see our molecule become more and more positively charged. Above that pH, we start to deprotonate, and it starts to have an increasingly negative charge. And for the sake of being thorough, let's do one more example. Remember my steps. Step 1, draw the molecule fully protonated. In this case, we're talking about our third example from the previous question, which is aspartate. Aspartate has 2 OHs and H3 plus. We leave them all protonated. Step 2, write down the pKa for each applicable group. What are those pKa values? Here they are. Step 3, if you have more than 2 pKa values, and we do in this case, then find the 2 that have the same charge as each other. So I've got these 2 neutral OHs, same charge as each other. This NH3 plus is the odd man out. The OHs are the ones I'm going to go with. Then all we do is calculate the average of those 2 pKa values. Here they are. That gives me an isoelectric point, or PI, of 2.98 for aspartate, which is also known as aspartic acid. Step 4 is remember what that means. It means that at pH 2.98, aspartate will have a net 0 charge. Below that pH, we start to see things get more and more protonated, which means we start to protonate these OHs and we see an increasingly positive charge. Above that pH, we start to deprotonate things. We get more and more O minuses, which means we start to see things get more and more negatively charged. And now I'll address our final concept from this PowerPoint lecture, that of electrophoresis. Electrophoresis is a technique that allows us to separate amino acids based on their PI, or isoelectric point values. Here's how it works. We put a mixture of different amino acids in the middle of a piece of paper or a gel. We then place this paper or gel between 2 electrodes in a solution that's buffered to a specific pH. Now we turn on the current. Simply put, amino acids that have isoelectric point, or PI values, that are more positive than the solution's pH will have an overall positive charge and will migrate toward the negative electrode. Amino acids with pI values that are below the solution's pH will have an overall negative charge and will migrate or feel attracted toward the positive electrode. To summarize this more simply, I've written up some crazy equations here. If pI, the isoelectric point for the amino acid in question, minus pH is positive, then the amino acid will be more positive. It will hence move toward the negative electrode because things that are positively charged are attracted towards negatively charged stuff. The converse is also true. If pI minus pH is negative, then the amino acid will be more negative. It will then move toward the positive electrode in electrophoresis. Let's take a look at an example. Let's pretend that I subject a mixed solution of arginine, alanine, and aspartate with these individual isoelectric point values to electrophoresis at pH 5. When I'm all done, where do each of these amino acids end up relative to each other? Let's see if we can figure this out. We begin by doing the math. Here's arginine. What I do is I take its isoelectric point and I subtract the pH of the solution, 5. And I end up getting this number, 5.76. That is a positive number. What does that mean? It means that when you run the electrophoresis, arginine is going to move toward the negative electrode. Alanine has this pI value. I subtract 5 from it, I end up with 1.02, which is also a positive number. Now 1.02 is obviously not as large a positive number as 5.76. What does that mean? It means that alanine will also move toward the negative electrode, but not by as much as arginine. Aspartate's pI value is 2.98. I subtract 5, I get negative 2.02, which is obviously a negative number. So what does that mean? It means that aspartate will migrate or be attracted toward the positive electrode. So arginine will move toward the negative electrode, alanine will as well, but not as far, and aspartate will move toward the positive electrode. Now I draw a picture. If we were to actually draw a picture depicting that movement, here's the center of our gel or of our piece of paper that we've placed this mixture of amino acids on. We've got the negatively charged electrode and the positively charged electrode on either end. What we see is arginine and alanine both have positive differences between their pIs and the pH of the solution. They migrate toward the negative end. Arginine, of course, by more because the difference is larger. And aspartate with a negative difference migrates toward the positive terminal. Hope that makes sense. This is the result that we would expect to see if we took this mixture and developed them in an electrophoresis test. Now once we finish doing the electrophoresis, we have to have some way of actually seeing the individual amino acids that have been electronically dragged across our paper or gel. How do we do that? Well, we stain them using a chemical compound called Ninhydrin. Now if you want to know more about how this works, please consult section 23.5. I will not require you to understand or know the mechanism by which Ninhydrin reacts with amino acids. I only want you to understand that Ninhydrin stains the amino acids on our paper or gel, much like a raspberry-flavored popsicle might stain your teeth, tongue, and gums. That's how we can actually see where the individual amino acids end up after we run them through electrophoresis. So now I arrive at a lecture example. I want you to predict the directions of migration toward the negative or positive electrode and the relative positions of each amino acid in the following mixture at pH 6, tryptophan, histidine, and arginine with their isoelectric values given. If you want, you can pause it at this stage, but of course you know that I am going to give you all the answers. So here we go. Once again, we begin by doing the math. The difference between tryptophan's isoelectric point and the pH is negative 0.11, which is a small negative number. Between histidine's, 1.59, a positive number. And between arginine's, 4.76, a positive number. What does that mean? It means that tryptophan will move toward the positive electrode, but just a tiny amount, because it's got this small negative number. Histidine will move toward the negative electrode. Arginine will as well, but by an even larger amount than histidine. So we would expect our gel to look something like this. Tryptophan just barely gets off the starting line. Histidine moves going toward the positive electrode. Histidine moves a little bit toward the negative. Arginine moves more. That's it. Do I expect you to know how to do this? Abso-freaking-lutely. So that concludes today's lecture on isoelectric points and electrophoresis. I hope you've enjoyed it. Are you hungry? I am. I'm going to go back to the kitchen now and get myself some food. So much food, in fact, that I will likely injure both my colon and my esophagus. So until next time, enjoy the rest of your day.